Okay, fine. Okay. Okay, so this is the geometric formulation of gravity. Okay, and the question is, why? Okay, so and the why is such a formulation possible? Okay, and why such a formulation not possible for other forces? Okay, so these are some of the issues we will look at before we actually start with the quantitative development of this subject. Okay, and anytime you have any thing, just you can.
Okay.
Hi, Rasha. Okay, hi. Hi. So, okay. So since Rasha has just joined, so I'll just tell her. So what I'm going to address is what is GR? It is basically geometric formulation of gravity. First of all, then I will address why such a formulation is possible in gravity. And second, why such a formulation is not possible in other forces. Okay. So these are some of the issues which we'll be addressing before we go to the quantitative formalism of this. Okay. Now, let us see what about Newtonian gravity. Now, what did the Newtonian gravity say? That first of all, it said that there was this thing about objects falling towards the earth, towards the ground, which is the famous apple falling from the tree, but one doesn't even know whether such a thing happened. Incidentally, there's some interesting story about this one. Do you know when Einstein uh, developed this? Under what circumstances?
During the
See, pardon?
during a pandemic, right?
Yes, exactly. See, what happened was when there were the plague years in England, then Cambridge had been closed, lockdown for 18 months. Then he had gone to his village. And in the village, he had actually formulated both the laws of motion as well as laws of gravity. I mean, so the moral of the story is the following, that colleges are inhibit creativity. So when there is a pandemic and he was at home, he did all these things. Okay, fine. So objects fall towards the ground, and then there is this moon going around the earth. And one of the big achievements of Newton was that he said it is that same gravity which is responsible for both. See, just imagine in those days, it was not at all obvious that the moon going around the earth should be the same reason why apple falls down. And so this we can look at it as one of the first attempts at unification of forces. It's just like the next big thing which happened in unification was Maxwell. He said that electricity and magnetism were faces of the same force, electromagnetic force. Okay, so this was one of the first examples of unification of forces. So what happens in Newtonian thing? In Newtonian formalism, it says that in free space, okay, that is no forces acting on a body particles travel in straight lines. Okay. And what is a straight line? Straight line is a geodesic of a free particle. Okay, so understand what a geodesic is, right? I mean, the path of minimum distance, and in free space or a free particle, straight line is a geodesic. Hence, in free space, particles, and now, although this may look like a hair splitting, but this is the crux of the whole thing about GTR. In free space, particles travel along geodesic. And in the presence of force, including gravity, particles do not travel along geodesics. Now, this was Newton in picture. And so basically it says that when I have a projectile motion under gravity, the reason it doesn't go along a straight line but falls along a parabolic path is because it is under gravity, so it's not a geodesic. So it need not. Okay, so before we proceed, let us just look at this a bit more. Now, consider, say, Newton's laws of motion. Second law. You say that force is proportional to acceleration. So F is proportional to A. And the proportionality constant is something which we define as mass. Okay. But we have to be careful about this mass. Here, what does mass do? Mass basically measures the inertia against motion of the system. Just stop me in case something is unclear. Okay. So here, this parameter mass is a parameter which is an inertia or something which, it's basically laziness. It doesn't want to change its state. So I want to call it MI. That is the inertial mass. Then there is Newton's law of gravity. Okay. Now, here what it says, so here it says that the force is equal to, it depends inverse of the distance between two masses, and there is a parameter which is the mass of a system which is gravitating. Okay. So, okay. And there is a constant G. So if suppose I have an object which has some mass, some parameter called here what is mass does not matter. Okay. Here it is just some parameter, some property of this particle. Okay. It may have nothing to do with this mass which is there. This is some property of the particle and the distance of this from R. And there is another particle which has a parameter which I call mass or the gravitational mass mg. So it means that this creates a field, and the test particle responds to this field through this parameter, which is called gravitational mass. Now, at the face of it, there is no reason why this mass and this mass should be same. So they need not be same. Okay, because the origin of these two are completely independent. One parameterizes how it pulls, another parameterizes if pushed, how it moves. Is this clear?
Yes, sir.
Okay, because at this stage, these are just two parameters of the system. Okay. Now, Mr. Galileo went to the Leaning Tower of Pisa and dropped two objects, and both of them came down at the same time. When is this possible? It is possible if, suppose, these two particles, the motion of these two particles under pure gravity do not depend upon the individual properties of these particles. That is, whether it is a chalk or a stone, doesn't matter. When you drop it, it will come down in the same way. You know, there was a very interesting thing which one guy was mentioning. Education is from Australia. I mean, probably he was a hardcore physicist and he disliked biology. He said that, look, we don't know, first of all, whether this experiment actually happened. But suppose this happened and Galileo had actually dropped these two balls. Clearly, they would not have come down at the same time.
Yes, sir.
They would not have come down at the same time because air resistance and so on. But here is where, I mean, in fact, this is something which you should remember while doing research. Here is where an intuition is required to distinguish the essentials from the non-essentials. See, he took the view that any small difference between them must have been because of air resistance, and hence he said that these two come at the same time if the air resistance was not there. And then this fellow added, suppose he was a biologist, he would have completely focused on the fact that they did not come down at the same time, developed an entire theory of why they did not come down at the same time, and in the process, missed out the whole issue of gravity. Okay. Anyway, so these two fall in the same way. Now, how is this possible? It's possible because suppose you equate these two now. Mi A is equal to, actually, I should have R. Okay. So let me just take just the magnitude now. Mi A is equal to Gmm by R square mg. Now, you can ask this mass, this mg is the mass of the object. Yeah, I should mention this. So this is motion of particle. Okay, I should say, okay. No. Rather, I will say that this thing is the force on mg by m. Okay. And since this force is on mg, this particle moves. Now, about this capital M, as I said, I may call it mass right now, but I do not care whether it is mass or any other parameter. For me, this Gm by R square is an agency, which is gravity, which makes mg move. So I don't have to bother about whether it's capital M is mg, mi, or anything else. Like, for example, suppose I have electromagnetism. Okay, then also this will be the electric field. Okay, so this is true for anything. But now these two are equal. Now this means R double dot, which is A, is equal to mg by mi, capital G, capital M by R square. Now, what does this mean? Okay, it's not a M into action into gravity. Let me call it G here. That's better. Okay. Now, the fact that the path was independent of the individual masses or individual things means that this R should not depend on the details of this ratio. What it means is, if for all particles, mg by mi is equal to a universal constant, then this will be equal to, say, some alpha. So R double dot will be equal to alpha mg by R square. And there is no reference to mg or mi of the particle. And since mg by mi is universal constant, R dot square same for all test particles. And I can, hey, what is the spelling of Galileo? I don't know if it is correct. Galileo's experiment explained. Do you understand the chain of logic here? What it says is, if your mg by mi ratio is same for all the objects in the universe, it means that for any object you take, this ratio will be the same. So my R double dot will be this. And so since alpha is a universal constant, nowhere it depends on the properties of the test particle. In particular, it does not depend on either the gravitational mass or the inertial mass of the test particle. Is that okay?
Yes, sir.
Okay, Anirudh, Rasha?
Yeah, got it. Yes.
Rasha, is it okay? Oh, yeah, okay, fine, yeah. Okay, fine. So now let us go further. Now I say that suppose if R dot equal to alpha m by R square, where alpha equal to mg by mi, I can redefine my alpha g as the new g, because I can absorb it in g. Right? And so I can actually from now on say R double dot is equal to capital G m by R square. This is equivalent to saying that I can take mg equal to mi with the new g identified with the observed gravitational constant. Is this okay? So in some sense, so there are two things here. One, mi is equal to mg, that there is no separate thing like inertial mass and gravitational mass. It is the same parameter mass. And mi or mg does not appear in the equation of motion of the particle. And this is the main pillar about which general relativity is built. If inertial and gravitational mass were different, then we will not be having this privilege. Somebody has put something in the chat. Okay, fine. Yeah. Okay. Right. Now, what does this mean? Okay, so if two particles are there, M1 and M2. So now on, what I will do is, I will not distinguish between Mi and Mg because I have taken to be equal. So I'll just call them mass. And suppose I have two particles of masses M1, M2. Okay. And position R1, R2. So the equation of motion for both these will be identical. Okay. Further, if suppose my equation of motion is identical, if initial conditions are same, this will imply that the trajectories are the same. Okay. Now, this has a very important implication. See, when we take it for granted some certain things. Suppose there is an astronomer astronaut who has gone into space and they are going around the Earth. And people do spacewalk. They come out of the thing, do some things and come back. Now, the spacecraft is one entity. The astronomy is any other entity. Suppose this was not true. Suppose the equation of motion for the astronaut and that of the spaceship, the equation of motion were not true, then it will be a disaster. Once they come out, both will be going on their own equation of motion and they will part ways. However, we see that when an astronaut comes out of the spaceship, both the spaceship and the astronaut actually go exactly the same way and he can easily walk back into the space or get back into the spaceship. The reason it happens is because of this fact that the equation of motion is independent of the masses of the system. So whether it is the spaceship or the astronaut, the equation of motion is the same. Since when the astronaut came out of the spaceship, both the position and velocity of the spaceship and the astronaut are identical. Their initial conditions are identical. In a differential equation, if the equation is the same and the initial conditions are the same, then the solutions are the same. So they follow the same trajectory. And hence, when the astronaut comes out, they are still together, although they are not physically bound to each other. Is this clear?
Yes, sir.
Yeah? Okay, fine. Okay. Right. So now this means that, okay, so now here the basic seeds of a geometric theory already lies in this. That is the trajectory. So suppose you just look at this M as an external agency. This trajectory is independent of the details. So the only thing it can depend is the geometry of the background. It does not have to depend on anything else. Now, let us now take it further. Okay. Let me just check if I have missed out something. Geometric theory. Yeah. So now let me look at the differences. Now, suppose, you see the 1 by r square thing, electrostatic also 1 by r square. What is the difference? Okay. So now if suppose I have a charge Q, capital Q, and another charge small q, and the distance r, then the okay, we know that force on Q is equal to mass of Q times the acceleration of Q. Okay. I'm just writing the magnitude because I'm just looking at radial motion. But the force on Q is also equal to 1 by 4 epsilon naught capital Q by R square times Q. Okay. So let me not call it, I'll just call it, instead of Q, I'll just call it M. This is the mass of Q. Now that I have said all this, there is no distinction between Mi and Mg. That is gravitational and inertial mass. Okay. And so I have from these two, Ma is equal to 1 by 4 epsilon naught capital Q by R square times Q. And so A, which is equal to R dot, is equal to 1 by 4 pi epsilon naught capital Q by R square times Q by M. Previously, it has Mg by Mi. Now it is Q by M. Now, if suppose I have a proton, I have plus E and mass of the proton. And if an electron, I have minus E and mass of the electron. And so the acceleration on a proton will be equal to 1 by 4 epsilon naught Q by R square E by, pardon? Hello, any problem?
No.
Okay. E by MP, and R double dot of an electron is 1 by 4 pi epsilon naught Q by R square minus E by ME. So even if we discount the fact that the charges are different, you find that this factor is not the same for electron and proton. And hence, the equation of motion of electron electron and that of proton are different in the same electric field. But since in the case of gravity, this cancels out. The equation of motion is same of any particle in a given gravitational field. Is this distinction clear?
Yes.
Okay. Okay. So, yeah, okay, fine. And that is why you cannot, so in the case of electrostatics, you need to know the mass and the charge to find the trajectory. In the case of gravity, I don't need to know any of these details. So it is more universal for all particles. Okay. Now, because of this, there are some very interesting consequences. Okay, so let me say, okay, plane in a lift. Now, what I do is, I do the following experiment. I have a lift and there is a person sitting in the lift and he has a particle which he has released and the lift is going down. Okay. Now, the position of this fellow or that is position will be equal to what is that? GT plus half. S is equal to UT plus half AT square. Yeah, will be half GT square. Okay. Of this observer, the R of this particle will also be half GT square because it is falling in the same gravitational field. And as I said, since the equation of motion of each of these persons does not depend on their masses or charge, both will fall in the same way. And hence, R naught minus RP is 0. So, no relative motion between particle and observer. Okay, in gravity. I have another experiment in which there is a particle, there is an observable, and no gravity. Once again, R naught minus RP is 0. No relative motion between the two. Okay. And hence, I will say looks like, and I will tell you that this is not completely true. Freely falling frame, here the lift frame, is equivalent to frame in no gravity. That is, it says that if suppose I have a lift and everything is closed and the person cannot see what is outside the lift and the lift is freely falling, this person cannot do an experiment with mechanics and find out whether the whole lift is falling under gravity or they are actually sitting in a gravity-free environment. Clear? Anirudh? Rasha?
Yes.
Okay. Fine. Okay, and fine. So, and why is it possible? This is possible because, again, as I repeat, the individual details of the particle and the observer and the lift does not play a role. The equation of motion of all three of them is the same given in the same gravity. And that is why this is there. Okay. So this, having done this, let us now see what is the implication of this independence of the details. So let us consider the following. Yeah. So suppose I have free particle on a flat surface. Free particle on a flat surface, then particle will travel in straight line. Okay. And why? That is because geodesics are straight lines on flat surface. Okay, so this is the first thing. Now, if I have a free particle on the surface of a sphere, then what will be the trajectory of the particle on the surface of a sphere, a free particle?
Geodesic.
So what is a geodesic? On the surface of a sphere?
A great circle.
A great circle. Along great circle. Okay, because great circle is a geodesic. Now I can turn the argument around. What it says is, if I analyze the nature of geodesic, it can tell you about my geometry. If the geodesic is straight line, I know that it is the geometry is flat. And the geodesic is great circle, I know the geodesic is the surface of a sphere. In other words, if the geodesic of a particle, of a free particle, is not a straight line, I know that the surface is not flat. Is that okay?
So when you say free particle, like why free particle?
Oh, because for example, suppose I have the following. I have a flat sheet. Okay, I have a particle, and then I keep suppose a particle is of charge Q, and I keep this with a charge Q, it won't be a straight line, it will be like this.
Okay. So without any other influence, any forces.
But it's a good question. When I say no other influence, there is a caveat here. You see, the particle is being constrained to move on the geometry. So you can say that there is some force which is keeping it on the surface. Right? Okay.
Yes,
so here what is being said is, there is no force acting along that surface. For example, if I tie a particle with a rope, the particle will go on the surface of a sphere. The force which is acting is not tangential to the surface, normal to the surface. So that is what is meant. So if suppose you say that the space in which, there is no force acting on the particle in the space in which it is moving. There is no force along the surface of the
Okay,
solid.
sir.
Okay? So that is what I mean by free particle. Okay. So now what it means is, moral of the story is, nature of geodesics of free particle are related to background geometry. And this is where we are building a case for geometric theory. Okay. Now, where does it come? Where does it, I mean, where is it that the general relativity comes in? Okay. Now, if you have, okay, so if suppose, take the case of electromagnetism. Electrostatics. Different particles travel along different trajectories. Trajectories, but it's important one thing, even with identical initial condition. See, of course, even if the initial conditions are different, they will be different. But here is something more. Even if the initial conditions are the same, because the equations motion are different, they will go in different trajectories. Okay, in electrostatics. Hence, geometrization not possible because if, or before that, let me talk about gravity itself. Then I'll tell this as this one. Okay. Now, if path of particles independent of particle properties, then path of particles is related to background geometry. Why is this so? If, okay, so, okay, because of the following reason, I'll just come to it. So, what Einstein said was the following. Einstein said that even in presence of gravity, particles go along geodesics. Okay? How? He said that, okay, for Newton said was, in gravity, uh, in gravity, okay, even in presence of gravity, space-time is flat. Particles do not go in straight line. Hence, particles do not follow geodesic, and okay, they move in a non-straight line. Now, what was Einstein's picture? Einstein said, that okay, he said that even in presence of gravity, particles move in geodesics. Okay, then the question arises, then why are they non-straight, the paths? For this, Einstein said, gravity modifies background geometry in such a way that the new non-straight path is the geodesic of the new geometry. Is this clear? This is the most important thing for this GTR.
Can you repeat this? I'm finding it difficult to understand.
Okay, no, this I will repeat because this is the central pillar of GTR. What Newton said was, whether there's gravity or not, space-time is flat. So he says that since so if the particle is free, it will go along geodesic. If gravity is acting on it, because of gravity, the particle will not go in a straight line and hence not along with geodesic. And this is the explanation he gave why a projectile goes in a parabolic path and not straight line. Is this clear? Newtonian thing?
So he says that, so according to Newton, the particles do not follow the geodesic.
You don't follow geodesic.
Gravity. Okay.
Okay. Now, what Einstein said was the following. He said, and it because since it does not depend. Okay, I will come to that. Now, what Einstein said was, even in gravity, particles still moves in a geodesic. Then the question is, why is it non-straight? Then he said, just like on the surface of a sphere, geodesic itself is a curved line. He said the geometry, the gravity modifies the background geometry in such a way that the new non-straight path which the particle is following is actually the geodesic of the new geometry. And hence it is still going in a
straight line concept comes
There's
only
no straight
from
line.
our perspective. Yeah, from our
Non-straight
perspective,
line.
it will be a straight line.
Pardon?
But if you look at it globally, then it will be a curved space, right? Because of gravity.
No, no, globally, it will be a non-straight line. See, locally, I can always draw a
Yeah,
tangent.
yeah, that's what.
Yeah. So an example is, suppose there is an insect on the surface of a sphere, on a surface, and it wants to know whether, it's a thought experiment, whether the surface is flat or not. The insect will follow a free particle and see whether it comes back to the original position or not. Right? So if it finds that the thing is non-straight, okay, or alternative, okay, so let us put it this way. Suppose I have a particle, okay, and what it's just a hypothetical thought experiment. Suppose I have a stone and it is moving along a circle. Okay. Now, if suppose any object is moving like that, what I will tell is that the particle itself is moving along a curved geometry. So that's the same thing here. It says that since all particles will follow the same trajectory under gravity, I can say that if the particle, if suppose there is gravity, I can alternatively say that the particle is still moving in a geodesic, but the geodesic is no more straight. That is the only thing. What does it mean by a geodesic not being straight? It means that the background geometry is not flat. And that is why it says
Okay.
in Einstein's theory, gravity curves geometry.
Okay.
Okay. Now, let us now look at it and analyze. Suppose the trajectories of the particles depended on the mass of the particle. What will it do? A particle of mass m1 will follow one geodesic. Particle of mass m2 will follow another geodesic. Okay? If the masses were different. But now I can't call them geodesic because, see, I can't have the geometry for particle 1 and geometry for particle 2. The background geometry has to be universal and valid for all particles. This is possible. So for making gravity geometrical, all particles should go in the same geodesic, and that is possible only when the path of particles is independent of mass. Is this logic clear?
Can you repeat it?
Yeah. So what I'm saying is, if suppose you want to attribute the path of a particle due to background geometry, then that has to be universally valid for all particles. You can't have geometry for one particle and another geometry for another particle. Both have to reside in the same geometry.
Okay.
Right? So this geometrization of gravity was possible essentially because the inertial mass and the gravitational mass were taken to be the same, and hence mass cancels out in the equation of motion for gravity. And that is why the background in which they travel is universal, and hence you can attribute it to a background geometry rather than individual particle properties.
So all particles will have the same geodesic in the same gravitational field.
Exactly.
Okay.
With the same initial conditions.
Okay.
Okay. And that is why I can alternatively say that let me not look at it as particles not going along geodesic. Since they are all going along the same path, I may as well call the new path as the geodesic of the geometry.
Okay.
Okay. And hence Einstein said that.
So geodesic would probably be a more collection of trajectories for different initial conditions.
Pardon, sorry?
So you can say geodesic is basically a collection of
No.
or a set of initial conditions. Sorry, a set of trajectories for different initial conditions.
What you're saying is, what are geodesics?
Yeah.
Geodesics Okay, in Newtonian language, geodesics are paths of free particle.
Yeah.
In Einstein theory, they are paths of quote unquote free particle because he does not look at gravity as a force. Unlike electrostatic, which is a force. So what Einstein said was, gravity is not a force. It is just bending the background geometry. And since the geometry is bent and the particle has to go in the geometry, so it goes along a curved trajectory. Is it clear, Rasha? Yajil?
Yes, sir.
Okay. Rasha?
Yes, sir.
Okay. No, sir. Huh? Okay. Okay. Fine. So this is the crux of it being a geometric picture. And as you see, you cannot do this in electromagnetism because you can't say geometry of electron and geometry of proton. Geometry is something which has to be common to all particles, and that is possible only when it is independent of the individual particles. Okay. So this is the basic thing about the philosophy behind geometrization of gravity. See, I'll make short notes on this and then circulate it the way I did in astrophysics thing. Okay. Rasha, by the way, since you are not, you said you will not be able to attend the astro, I have shared the notes of astrophysics. So in case you are interested, you can take it from Anirudh or Yedid.
Sure, I would love that. Thank you.
Okay, yeah. So, right. So now, yeah, that is correct. So now, what does it say? It means that the mechanical dynamics of particles is independent of, is universal for all particles. Okay. And so this is called the weak equivalence principle. Okay. That is, in the presence of gravity, the all particles move along the same way. Now comes the major, what I would call a hypothesis, which Einstein said. We have said everything about particle mechanics. Now, Einstein made the first guess. He said that maybe not only laws of mechanics are same in the presence of gravity, all laws of physics are same in the presence of gravity. And this is called the strong equivalence principle. That is, and when I come to formalism, we will see how it unfolds in the formalism of general relativity. But basically, it means that in some sense, Maxwell's equations are also, which are valid in flat space-time, will also be valid in curved space-time. That is, in the presence of gravity. Is this clear?
See, can you say it again?
So what I'm saying is, as far as mechanics is concerned, from Galileo's experiments and all, one has argued that laws of mechanics are the same whether they are in free space or in the presence of gravity. Right? Because they all follow the same trajectory. Because so now I'll say laws of mechanics is, if there is no non-gravitational force, particles will travel along geodesic. Now, this is a universal statement. If there is no non-gravitational force, that is, whether it is free particle or gravity, it does not matter. It will still travel along a geodesic. That's what Einstein, from all this, which is what we have got, which I argued just now, right? So it means laws of mechanics are independent of whether you have gravity or not. Now Einstein made the first hypothesis. He said, maybe, suppose we say, not only laws of mechanics, all laws are same, whether in the gravity or without gravity. Okay. Now, while weak, so this is called the strong equivalence principle. That is,
Just like just like we have in special theory of relativity, there we observe it for all inertial observers. Right?
exactly.
Uh,
Yes, yes. Just like you say that, yeah, exactly. That's a good example. In special relativity, we say that all laws are same, whether they are compared to something, whether they are at rest or in a frame moving uniform speed. Here it says all laws are same, whether they are in the presence of gravity or in the absence of gravity. This is called the strong equivalence principle, as against saying laws of mechanics are the same in gravity or without gravity is the weak equivalence principle. And it is the strong equivalence principle which was a major step for formulating general relativity.
Yes, sir.
Okay, yeah. Fine, okay. So you say that laws of physics same with or without gravity. And in the language of Einstein, laws of physics same in flat geometry or curved geometry. Now, I should say what is curved geometry. Now, here when I say geometry, it does not mean just spatial geometry. Now, in the spirit of relativity, my geometry consists of 4 coordinates: X, Y, Z, and T. It is in this, so it means that, let us see. Yeah. Okay, I'll come to, okay, I'll come to that. But broadly, it is, you should remember that when I say now geometry, it means geometry in 4 dimensions, X, Y, Z, and T. And that it is no more what I would call Minkowski space. If it is Minkowski, it is flat. It is equivalent to, okay. So just like Pythagoras theorem is valid on a flat surface, you have dt square minus dx square minus dy square minus dz square equal to ds square is invariant. Eril, you have done this, right? Anirudh and
yes.
Rasha? You must have done this, right? Special relativity.
No, Shesh, I haven't done this.
I see. Okay.
I have. I've done it. In my master's, yes.
Okay. Right. So, okay. So as we go, so Rasha, we will do one thing. Maybe we can sit down together and then I can tell you sometime about this one to make up for it. Is that okay?
Sure. And also, I'm able to follow this.
No. Now what will be coming will be a bit this one, but
Okay.
we will manage that. Okay. Right. So this is the whole crux of the approach to this. Okay, fine. Now, the other thing is the following. We know that in special relativity, you look at time and space as a unified thing. You don't distinguish between them. Okay. And okay, so let me just make some more points here, which are important. Now, we talked about 2 different systems. One is electromagnetism and gravity. The similarity is, so I wouldn't say electromagnetism, I call it electrostatics. The similarity is that this is also 1 by r square. This is also 1 by r square. Okay. What is the difference? Yeah.
Earlier, when they asked to ask us what is the difference between gravity and electrostatic, first we used to say that electrostatic is either attractive or repulsive, and
I'm coming
gravity
to
is
that.
on.
I'm coming. That's
But
why
then,
I'm coming to the difference.
okay, sir.
Okay. In here, we have two types of charges, plus and minus. Here you have only one type of charge, which is positive mass. There is nothing called a negative mass.
Mhm.
And the second is like charges repel. Here, like charges attract. Okay. But now there is one very big difference which will come and hit you in GTR, general relativity, and which is in the case of electromagnetism, charges produce field, but field themselves are neutral objects. They don't have charge, right? So fields, do you understand this? So see, if I have, okay, so fields, okay, okay. So fields, not source of gravity, a source of electrostatics. I mean, this may appear a bit vague, but it will be clear once I mention the thing about gravity. So do you understand this? Charges produce fields, but field is not positive or negative. So field is only an intermediary for conveying the interaction, but it itself is not a source of interaction. Is that clear?
Yes.
I mean, for example, suppose I have okay, so suppose I have two plates, plus and minus far away, and there's a strong field between them in a capacitor. Okay. Now, if I have a charged particle, it will not get attracted to the field. Field will push it towards the charged particle, but it will not go towards the field. Unlike it will go towards the charged particle, other charged particle, positive or negative. So the source of the field and the agent which communicates this force are two different objects. The agent, which is field, which communicates this force, is not a source of that, is not a source of that force. Is this clear? You don't have a positive electric field and a negative electric field, but you have positive charge and negative charge.
So, but the direction will be different, right?
Direction may be different.
Sir, I don't see the difference.
No, the difference is this. You see, let me put it this way. Okay, so let me put it this way. Let us consider the Poisson equation.
Hmm.
Okay, some epsilon naught or whatever. This rho is some charges. This produces a potential.
Hmm.
But this potential does not create more charge to produce force.
Okay.
Okay. But now look what happens in a Newtonian aspect of gravity. I have del square equal to phi equal to 4 pi rho. This is a mass. Now rho produces phi, but now there is a catch. The moment you get to special relativity, any energy density is equivalent to mass. So this field, which has energy density, will again produce more amount of source, unlike this case. In other words, charges produce electric field, but electric field does not produce more electric field. However, in the case of gravity, if you just marry Newtonian gravity and special relativity, you get into a problem because mass produces gravitational field. Gravitational field has gravitational potential energy. But then since energy and mass are equivalent, again it feeds back to the right side to produce more field. Is this clear?
So any example?
No. This is the example. I mean, the point is, okay, I will tell you how it manifests itself, but do you understand this?
Yeah, I understand the point.
Okay. Now, the reason, as a result, here, when I say this word, both Rasha and Anirudh will get very thrilled. Because of this, it produces a non-linear effect. Okay. So see, it's because of this positive feedback kind of a thing. That is mass. So it means that I cannot say, if I want to have special relativity and Newton gravity together, I can't say so much mass has produced so much field. I have to do a self-consistent thing. There is a mass, it produces field. The field has energy. Energy and mass are equivalent. So it corrects further to the mass it is producing. This produces more field. Field produces more energy. Energy is mass. So there is a further correction. Whereas, in the case of electromagnetism, it doesn't happen. As a result, electromagnetic equations are linear equations like Maxwell's equations. Gravitational equations, when you do it in a space-time manner, the way Einstein said, because of this, they will be nonlinear equations. And this is the example what Yeril was asking. The fact that gravitational equations you will find will be nonlinear equations is because fundamentally that this feedback is happening in gravity, does not happen in electromagnetism. Is this clear?
Yes, sir.
Can you explain the feedback part again? I'm a bit lost.
The feedback part is basically that in gravity, okay, rho produces field, field produces gravitational energy because the field has energy. And energy is equivalent to mass. And hence it produces more gravity. Okay. In the case of charges, these produce, say, electric potential. This leads to electric potential energy. Now, this may lead to mass, but there is nothing like mass producing more charge. And so it does not act on itself. See, mass may produce gravity, but it can't produce electric field. Yeah, please ask me because it's a very tricky thing.
Yeah, got it.
Is it clear?
Yeah, clear.
Rasha?
Yeah, clear.
Okay. And Aiden?
Sir, I have a question, sir. We have Dirac equation, right? Dirac basically made, time and space were at different footing. So he made something, so he linearized the equation. Is this something similar to that,
No,
or
no, no, no,
the
no, no, no.
equations don't?
No, 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 no,
Hmm.
no, no. You see, there is a
How?
difference. In
How?
Dirac equation and all those things,
Hmm.
you talk about field in a gravitational field. But you know, there is another one's happening. You know, it is like, okay, so given a geometry, it tells you how the particle moves.
Hmm.
But how the particle moves again tells how the geometry should bend.
Hmm. Hmm.
So, you know, that is
This
what
is
is told famously about gravity.
okay.
Gravity tells particles how to move, and particles tell gravity how to bend. Okay? And so there is this, together thing which is acting, because of which there is a nonlinearity.
Okay.
Unlike the case of electromagnetism, if I have a charge, if I have a field, okay, so if I have a field, if I have a charge, no, if I have a field, it tells my charge how to move.
Hmm.
But this thing does not produce more field. I mean, the energy density of this does not produce more field.
Yes, yes.
Okay. Now, I'm not sure, but you know, in some sense, I think this is similar to what happens in quarks inside
Hmm.
protons. See, what happens in quarks is quarks are mediated by gluons.
Hmm.
Gluons themselves have charges.
Hmm.
And so this kind of a nonlinearity could be happening there.
Yes, yes.
Whereas in the case, okay, suppose you want to look at it from a quantum level, that's a good way of looking at it. You know that electrostatics or electromagnetism is mediated by photons.
Hmm.
But photons are not charged. So photons don't produce electric field.
Hmm.
Whereas in the case of gravity, from a graviton kind of a point of view, you want to see, gravity is mediated by gravitons, but gravitons have energy and they produce further gravitons.
Hmm. Okay.
And that's where the nonlinearity comes in gravity.
Yes.
And
Yes.
that is why Einstein's theory to solve is much more complicated than
Hmm.
the electromagnetic theory of Maxwell, because it is at least linear.
Hmm.
Is that okay?
Yes, sir.
Okay. So I will just tell some more things and then I will stop.
Hmm.
Now, so suppose you take electromagnetism. Let us do first of all a patchwork to formulate a geometric theory of gravity. I can say, okay, suppose I have, okay, rather than saying, I will say marrying special relativity to Newtonian gravity. This is the simplest extension you may try to do. And I will tell you why it fails. Now, in the case of, Newtonian gravity, I have del square phi equal to rho. Okay. Now, if suppose I want to make it into special relativity, I can say, let me guess this. Box phi equal to rho. Okay, just like from Laplacian thing, I go to Klein-Gordon equation. Right? So I say, can this be true? Okay, let's see this. But there's a bit of a problem here. The problem is this. This is a scalar object, whereas density in special relativity is not scalar. It depends on the frame. Why? To see it in a very simple way, suppose you have something moving at some velocity, there is a length contraction. So it means the density increases because the volume is contracting for the same mass.
Hmm.
It means that rho is a scalar in rotation or translation or Galilean transformation. But under Lorentz transformation, rho is not a scalar. But the left-hand side is a scalar under Lorentz transformation. It means that there is something wrong in this equation. So this generalization cannot be done. Actually, what happens is there is something called the energy momentum tensor, which I will come to during the course, in which rho is actually a component of T00, which is a 0, component of a tensor called Tij. So I would say that maybe phi equal to T00, but this cannot be there because you just have a component of a tensor and a scalar. So I should say that maybe the equation is something like this, some object like this, in which the 0, component is what we see in box phi equal to rho. And now in box phi equal to rho, what happens? I have 1 by c square del 2 by del t square minus del square acting on phi equal to rho. And in the limit of, so this is equal to box phi. In the limit of c going to infinity, this goes to 0 and box goes to del square, and I go back to this Poisson equation. That is, now here I am not deriving something. I'm just sampling various things to see whether there can be some patchwork possible to connect all this. So suppose I say suppose that my actual equations of gravity is actually box times some object phi ij, which is equal to some object Tij. So that both sides are tensors. Right now, you look at it as both sides are matrices. I will come to tensors and scalars later. And I say that what I call rho is basically T00. And what I call phi is actually phi 00. And so this becomes phi, that is, the 0, component of these objects is phi and rho. So I have box phi equal to rho. And the limit of c tending to infinity, 1 by c square tends to 0, and 1 by c square del 2 by del t square minus del square tends to minus del square. And so box tends to del square. And I get back the Poisson equation. This could be one of the approaches one could take. But again, this is a problem because of what I mentioned. The moment I do that, I need to take a correction of this and feed it back, because in gravity, there is a nonlinearity. Now, it turns out that when you actually do the full Einstein's equation and take the weak field limit, you will indeed come to this kind of a thing. But when you have strong gravity, because of nonlinearity, this cannot be a complete picture of gravity. And that is why you need to look at this entire issue of gravity completely from a fundamental level and formulate it. It cannot be done by some patchwork of Newtonian gravity being incorporated into special relativity. Is this okay?
Okay.
Yes.
Can you just repeat?
Huh? Yes,
Can you just repeat the last part which you said?
What I said last part was, so what all this shows is that by taking Newtonian gravity and somehow by force doing some jugaad, incorporating in special relativity, we may be able to achieve some weak field limit, but we cannot get a full theory of gravity in this way. We will have to look at this entire issue from basic fundamentals. After we make a complete theory of gravity, one may ask a question. Is all this which we showed recoverable in the weak gravity limit? The answer is yes.
Okay.
I think I will stop now. So, first of all, is some kind of a, heuristic motivation clear as to why a geometric theory is, first, not needed, why a geometric theory is admissible? Geometric theory is admissible. Why? Because of that first thing, that trajectories of particles in pure gravity are independent of the mass of the particle. And that is where we started.
Okay.
Okay. Yajil, Rasha?
Yes, sir.
I think Rasha has gone home.
Yes, Tish. I'm
Okay, yes, joking. Okay. So I will end this here. Now, what I will do in next time is to say that fine, I know that it is geometry. So first of all, I will prepare the mathematical machinery for attacking this problem as a geometric problem. So that is what I will do in the next class. In the next class, it may appear that I'm doing something disconnected with anything about physics. Just bear with me. I will just put all the machinery in place so that I can start using it for everything which I want. Okay?
So basically tensor algebra.
Tensor algebra, exactly.
Okay. So,
yeah.
when you differentiated gravity and electrostatic force, you said, I mean, gravity cannot be repulsive. But then while we were in workshop, you said there could be a negative gravitational term, right?
Okay. Yes. I didn't say gravity cannot be repulsive. I said that mass cannot be negative, which is different. You see, the repulsive gravitational term, again, will be the same repulsion whether it is for every positive mass also and independent of mass. That is, even the repulsion term will be independent of mass.
Yeah.
Okay? So, even when there's a repulsion term, it will not violate the principle of equivalence. Just like the attractive gravity has a parameter m, the repulsion will also have a parameter m, which will cancel from both sides. And hence, the trajectory of particles, even under repulsive component of gravity, will be independent of the mass of the particle. Same repulsion for all particles.
Okay, sir.
Is that okay? Yeah. Okay. So, okay, just so next, okay, Yadil, I mean, I understand you have got the exam, but Anirudh and Rasha, so will Thursday be a good time?
Yeah, Thursday would work for me.
Yes.
And which will be will 11 to 1 be a good time? No.
No, mornings are difficult.
Okay. So we will keep it as 3 to 5 on Thursdays.
Yeah,
Okay.
that's a good.
Sure.
Okay. And yeah, just what is that person's name? You said, I forgot the name. Jennifer.
Yeah. Well,
just tell her if there's any problem. Has she got my messages or not? I don't know, because I had added her in that group.
For astro classes?
No. I mean, for this, for GTR, she wanted to come, right, Jennifer? Or who was it? Somebody you said was interested.
No, that was Rasha's friend, right? Rasha's friend.
No. Rasha's friend for astro, I thought. Hey, wait, I'm confused. Just a minute.
No, Jennifer is the one who suggested for astro classes. She wanted to come for astro classes and she forgot to come this week.
Oh, no. Yeah. That is it. Pitambar.
Yeah. Pitambar, yeah, I don't know. I talked to him, he got my message. He said he got the email, but
Okay.
I don't know why he it.
Okay.
I'll remind him, no problem. I'll just update him.
So what I want is the following. Okay. So let me give you people some work. All three of you. Ariel, I have already done. See, I am writing a book on GTR.
Okay.
And I'm incorporating all these things which I said in detail. I will send to three of you the portions which are relevant to what we did.
Okay.
Go through it critically.
Okay.
And if needed, tell me I'm wrong.
If needed. Okay.
Okay. No. Be critical about it.
Yeah, okay.
Be critical
Sure,
about it.
definitely.
Not only about the matter, but if suppose you feel that something is not expressed in the best possible way, just let me know. Because I am writing that book essentially for people who have not had any exposition to GTR before, including terrorism. Okay. Acha, that is one thing. Rasha, do you want to discuss special relativity sometime?
Sure, but when will you be free?
You tell me, because or should we just keep a recap of some basic issues of special relativity next time?
Yes, sir.
Yeah.
Anirudh?
Yeah, sure. No problem.
Okay. I mean, when I say special relativity, I am not talking about a person going in the train and looking at something. I actually mean formulating it using 4-vector and so on.
Okay, that will be perfect, because I have ideas of special relativity, but not the mathematics. So
okay, so we will do that. So what we'll do is next time we will do this. The next time we will do about tensors.
Okay.
Okay. Okay. Chalo.
Sir, I think my classmate, she'll also be interested. So I'll ask her to mail you.
Yeah. No problem.
Okay.
Hey, Yeril, when is the exam getting over? 24th or something, right?
22nd.
22nd. So I think regularly you will be able to join only in January. Okay. Next Thursday, are you free?
Next Thursday. If it's from 3 to 4, I'm free. I'm available.
Yeah. But Yeril, as I keep on emphasizing, don't sacrifice your exams for this. This can wait. Exams you will have to do. Okay? So don't be lax on the exams. Yeah.
Yes, sir.
Okay. I mean, there are some, to succeed in life, you have to do some things you don't want. We have to do some things you don't want to do. Exams are wrong. Exams are the most painful thing. Exams are an example of things which are painful, not only person who writes the exam, who corrects the papers also. No? The only people who have the sadistic pleasure of administering exams is the exam branch of the university. Okay. Okay. Chalo. Bye. Thanks.
Bye.
Thank you.